Okay, let's get started with the types of problems that we can do involving acid-base equilibria. Ultimately, these problems are just like the equilibrium problems that we did in chapter 14. You've got a reactant side, a product side. You can write an equilibrium constant, all right? So that means there's two types of problems: finding that equilibrium constant or using it to find the equilibrium conditions. Really, we're doing the exact same types of problems, but now we're in this world of acid-base chemistry. So one of the layers that we add to that is usually, instead of find the equilibrium conditions in terms of concentration, find them in terms of pH. All right? And so that's the most common way that you'll see the question asked. We just have to do a bunch of examples. So let's start with an example of a weak acid equilibrium. HClO, hypochlorous acid, has a pKa. We just talked about these P values. So this is going to be a measure of the strength of our acid of 7.45. Let's determine the pH of a 0.115 molar solution of HClO. If you haven't picked this hint up yet, anytime the language of pH is involved, implicit is that water is part of your system. So that tells you the other component that you're dealing with is HClO plus water. Okay? That has to be the case. Right? The pH scale only works in water because it's about the two pieces of water, H3O and OH minus. All right? So, like we had just finished doing in class, we can write a reaction. HClO is going to be our acid, right? Indicated pretty much because of we're told a pKa for it. All right, so that the A is a subtle hint. Hey, this is an acidic thing. So we're making H3O plus, and what we'll have is ClO minus left over. So the pH is a measure of how much H3O we have at equilibrium. So that's ultimately what we're after, is the equilibrium concentration of H3O. Last chapter, we would have done this problem, find the amount of H3O in a 0.115 molar solution of HClO once it has reached equilibrium. That's how the problem would have been worded last chapter, and then I would have told you the equilibrium constant. So now it's really the same thing, but we're going to have to find the equilibrium constant first from the pKa being 7.45. So the Ka is 10 to the negative 7.45, which is, in this case, 3.5 times 10 to the negative 8. Size of the equilibrium constant is an important consideration, just like it was last chapter. Small enough that we're going to use the approximation method in this table we're about to set up. So we're beginning with 0.115 molar HClO. How much H3O and ClO minus should I begin with? 0, right? Technically, there is a teeny tiny amount of H3O there because this is in water, so water would have undergone, its own equilibrium, 1 times 10 to the negative 7, but that is so small that it's not worth considering. Okay? So it's fair to assume, sort of the same way we had in the last chapter, that unless it's mentioned, those start out as 0. So this reaction has to proceed to the right side. So we would decrease the reactant and increase the products. So these will each be X at equilibrium, and this is 0.115 molar because our K is so small, as I just said. Set up the equilibrium problem to solve it then. Product H3O times ClO minus divided by HClO. So your Ka is 3.5 times 10 to the negative 8 equals x squared over 0.115. You're going to see this solution or this setup again and again, just so you know. Because so many of our acids and bases have small Ka and Kb values that you will always be able to ignore the X on the reactant side, which leads to just putting the reactant concentration here. And another benefit I've been trying to say in some of the lectures, we're only going to have coefficients of 1. So we don't have any more 2x and then that beats 2x squared, any of that business. It's always going to be x times x. It's going to be over and over again. These problems should be very, very easy to set up and solve. So we multiply by the 0.115, we take the square root, and x is 6.3 times 10 to the negative 5. Now here's where we get into the language of acid-base chemistry. We sort of would have stopped there last chapter and said, okay, that's the concentration of, in this case, H3O and the ClO minus. But so often in acid-base chemistry, we're interested in the pH. So now we can quickly turn our H3O plus concentration into pH by taking the negative log of it. And that will give us a 4.20 as our pH value. Remember the rule about significant figures? I think I got into this at the tail end of the lecture series introducing this chapter. There are two significant figures in 6.3 times 10 to the negative 5. And when you take a logarithm, the number out front comes from the power of 10. So it's the numbers after the decimal point that are connected as the sig figs. So the 2 and the 0 are the sig figs in this case. All right? Are there any questions on that one? Now if we change it to a base, let's do a base problem. Pyridine is a weak base whose Kb equals 1.7 times 10 to the negative 9. Find the pH of 1.15 molar pyridine. Now we're working with a base instead of an acid, and the main effect of that is it's going to change the reaction that we use for setting up our equilibrium table, and it actually is going to add one layer to the problem. Now I don't have the formula for pyridine like I did in the last example with HClO, hypochlorous acid, so that's not a problem. As long as I know it's a base, I can just generically represent it as B, something as a placeholder for what's happening. What will a base do in water? It will gain a proton, taking that proton from water, turning it into OH minus, forming conjugate acid. In this case, we would call this the pyridium ion. Okay, just so you know. Okay. So we're being told we're starting with 1.15 molar pyridine. We're not told anything about these other ions, so our safe assumption is that they're 0 initially. So again, because we have nothing on the product side, this is, I hate to be saying it's becoming automatic, but it really should be fairly straightforward. This would have to decrease in order to populate these ions on the product side some small amount. That equilibrium constant is very small, So our concentration of base will be essentially the same at equilibrium. This time we have a Kb, not a Ka. And it is found by taking the OH times the BH divided by the base concentration. So the Kb was the 1.7 times 10 to the negative 9, x squared over 1.15. It's that same format that I was referring to, right? You know, the x's are going to be our products, and there's no coefficients other than 1, so it's just going to be x squared over the initial concentration equals your K value. Multiply the 1.15 to the left, take the square root. X will be 4.42 times 10 to the negative 5. But what is x this time? It's not the same thing it was last time. X represents OH this time. And so that's a classic little stumbling point that some students fall over, is they always think the x is h, and then they just take the negative log and think they're done. We can take the negative log, but when we do that, we're getting the POH of this solution. So that's the negative log of 4.42 times 10 to the negative 5th. So the POH is 4.35. See, if you accidentally just thought you were getting the pH, you should be able to catch yourself on this problem. Because of the nature of this substance. Yeah, go ahead. What you got?
Because it's base, it should be higher.
Right. Because it's a base, the final pH should be above 7. Right? We know that pH scale, 7 is the middle of it. Acids are low pH, bases are high. So if you mistook what you were doing and thought you were done, you should at least reconcile that answer with the pH scale and what you know about it. This is a low pH, which does not make, or a low p-value, which does not make sense for a base. So, and that's because we forgot this last step. pH plus POH equals 14. So pH is 14 minus the POH, which would be 9.65. Now, we've at least got an answer that's above 7, and it makes some sense to us. All right. Okay. So again, very, very similar in the mechanics of the problem. What the table looks like, you know, starting with the zeros for the product sides, increasing by x, keeping the reactant concentration essentially the same. But, you know, key difference of using the Kb and then what the x represents and understanding what it means when you solve the problem. Now, we spent some time in the most recent lecture talking about salts and recognizing salts as acidic or basic in nature. But we can do more than just say that a salt, like calcium hypochlorite was one of our examples, is going to be basic. We could go ahead and actually figure out the pH that should result from adding a salt into a solution of water, because as soon as we know the Kb or the Ka, we can do a problem just like these two that we've done. All right? So I think this will be the last example that we do for now. Okay, it's the wordiest one. 10.8 grams of sodium cyanide. Which is NaCN, are dissolved in enough water to make 500 milliliters of solution. What is the resulting pH? There's a lot that goes into this problem. Okay. Ultimately, it's going to be an acid-base equilibrium. But because we're being given like mass, okay, and volume here, there's some stoichiometry that has to get done. This is a salt, so we have to figure out the nature of the salt, which helps us decide what type of reaction to set up. So those are all the thoughts that need to run through your head when you're presented a problem. What kind of substance is it? All right. What's the information I have? Ultimately, you're trying to get to a reaction table, but before you just jump at some conclusions and set up the wrong one, you want to think about the material. Okay. So let's start with NaCN. Okay. It's a salt. So what's it going to do in water? It's going to dissociate to Na plus and Cn minus. Okay. When we learned about salts, we said, okay, ignore our group 1 and 2 metals. And it's not on our Ka chart. Okay? But Cn minus has a Kb. So this is going to be a basic salt, and the Kb is 2.5 times 10 to the negative 5. So that's handy information for a little bit later. Now we also need to figure out, well, how much cyanide ion do we have? What's the concentration? So now we have to do our stoichiometry. While I'm going to ignore the sodium when it comes to the pH calculation, I cannot ignore it when it comes to the mass, because some of this 10.8 grams comes from sodium that's in there. So I can't get rid of it yet. And I'll show you how we do that. Okay. So this is just like we learned how to calculate any solution concentration, you do for lab or that you did in Chem 1. We need the molar mass of sodium cyanide. It's going to be 49.01 grams. Now the way that we can technically get rid of the sodium ion for any further calculations is to understand that each mole of NaCN will yield, when it dissociates, 1 mole of Cn minus from this dissociation reaction that we wrote for ourselves up here. Okay. Usually that's going to be the case, unless you had like a Cn2, parentheses, since you had a 2 subscript. Usually we look at 1-to-1s. So I have 0.2204 moles of cyanide ion now. So the concentration of my cyanide ion will be the 0.2204 moles divided by 0.5 liters. Right? My 500 milliliters is half a liter. So this is the molar concentration, 0.441 molar Cn minus. So we've done a little bit of work, and our question could now be restated. What will be the pH of 0.441 molar cyanide solution? Okay? It really doesn't matter what else came in with it. It's the 0.441 molar cyanide that's going to dictate the pH. This is now just like the last example that we did with the base. Okay? So let's set up a reaction of cyanide ion with water. It's going to make OH minus and HCN. Okay. Again, this is a base. We already identified that it's a base because it has a Kb. That's how I decided to make OH as the product. Initial concentration of cyanide is what we just worked to find, 0.441, 0, and 0. Now, I guess maybe I've been going a little bit quickly, but I've ignored water, right, in all of these 3 examples because it's not part of our equilibrium constant. We don't need it, so we just totally don't need to write anything for it. Okay? That's fine. All right, what's going to happen? Minus x plus x plus x. So these are each x's. Our k is small enough, especially compared to this starting value, that we can ignore the loss of x on the cyanide side. Write your expression, your equilibrium constant expression for Kb. Products OH and HCN divided by the cyanide ion. Now you're ready to put your numbers in. 2.5 times 10 to the negative 5 is Kb. X squared, again, in the numerator, over 0.441. Multiply that denominator to the left. Take the square root. X is 0.00332 molar. Look at your chart. Make sure you understand what X is. It is OH minus. Again, because we're working with a base. So when we take the log value, we have a POH. Our POH is 2.48. Thus, our pH, to finish this problem out, it's going to be 14 minus that POH, 11.52. There are, of course, a couple other varieties of problems. I'll briefly mention them. Each of these fit into the category of use the equilibrium constant to find something about equilibrium. And the other area would be find the equilibrium constant. And in acid-base settings, you're usually being told what the pH is at equilibrium. And so that's basically populating these bottom numbers for you. And then you work backwards to figure out how everything has changed. And then you would plug your actual numbers in to get your Ka or your Kb, whichever it might be the case for. All right? And on the review sheet or the problem set that I've set up for you in my fact data folder, there's also a problem that deals with what's called percent ionization. All right? Just a different way of describing how much of the acid or base has actually reacted and moved over to this side. We could calculate the percent ionization of this cyanide, in this case, by taking this number divided by the original value times by 100, because this is the loss of our cyanide ion. Right? So that would be less than 1%, I think, in this case, 0.004. Yeah, so it would be less than 1%, about 0.75% probably. So it's pretty low for weak acids. When you start to get like even 5%, that starts to become a pretty strong acid that you're dealing with in that case. All right, so the three problems that I've given you here, I think, are a pretty good leg up on the problem set. And that's only a portion of the problems in the problem set that involve these. Right? But you guys should be in a pretty good position now to independently work on the set of problems that I've placed in my fact data folder for you.